Hello, Friday, January the 19th, 2021. I think it's a week after I finished problem 17. I spent it repeating the work, going through the various, that's the full modular group, the various, let's take this one, the Hecke subgroup, the various subgroups of the full modular group, and then deriving the sums of the roots, or orders of the roots. And like this one, we can move this part to the right, so we get a nice circle here. So we can map this to this using S. So we go down here to the cusp, down here again to the same cusp. The ramification index of infinity is 2, and of naught is unity. I computed all the ramification indices of these groups, and then the sum, we get -2 at the integral from, or the sum, the integral from 1/2 to minus, this is weird, it's 1/2 to minus 3/2. I just didn't write that. And that gives the order of the root at infinity. That's here, yes. And then this one, we only get half a circle around. So that's 1/2 times it here. And then the cusp at unity, you get once, and then the sum of the interior points, and then this integral cancels this except for the integral from here to here of 1 divided by z. That's a quarter of a circle, so that gives k4. It's the same all the way through, so after a while it became an industry. This one, we had about the same problem that I didn't want to solve in problem 17, and that's how do we cancel this? And actually this cried out to me, I want to be symmetrized. So I could map this guy over to this guy. I don't know exactly, I've forgotten how. And then we got this fundamental domain, and now it's very simple. We go from here to here, and there's a cusp at 0, and then Q gets a factor 1/2. And then this one is not so interesting because it's isomorphic to gamma naught. I did it anyway. And then this one I found interesting. This maps to this, I guess by G, and this 1/3 of a circumvention, so it gives k3rd. And then at Q, which is the same as this guy, it's pi3rd, pi3rd. So that's together a 3rd circumvention, so it's 1/3 the root here. That gives rise to the possibility that k is unity. Of course not gamma naught of 3, because M1 just is the naught space here. But gamma 1 is generated by these two guys. It has the same fundamental domain because it's just plus minus this guy, plus minus identity or take minus identity, then you have generated the full group. But it gives the same fundamental domain. So I think it might be possible to find a modular form of order 1 of this group. Then we have gamma in order 4 that we worked so hard on. It sounds a little boring, but sometimes it isn't really. So it's in particular the cos condition. And the same with G. And we have the cusp conditions. Q capital N to N. And the same for G with Bn. So we go ahead and we split it up. Oh, I forgot the and taking this guy gives actually I already did this in my head, chi1, chi2 of D. Yeah, that's what we had to show. Right. And then the cusp condition. And then it's just the product of them, so that's okay. So it was boring. And now for B. The unique character, of course, is the one that when D is we are in gamma naught of level 4, so A is either A and D. The product of A and D is equivalent to 1 modular 4, so that means they're both equivalent to 1 or to modular 3. There wasn't room for writing the condition. I'm sure you could do that. This actually strikes a strange chord with me. It's a little strange. So we have to show that, I don't think we have to show that at least. Well, I would like to show, of course, that theta squared lies in gamma 1 of 4. And then afterwards, that gamma 1 of, which one do we need to get? It's minus unity. Isn't that obvious if we have proven this? Because gamma 1 of 4 equals, I think we have shown this before, actually. I'll just take a look. The lower part here, I was thinking, is actually proposition 29. And this is proposition 30. So B has been done, really. Now, what I don't understand is the number of zeros here. You see, what bothers me is that we have proven this in problem 17 together with this, and I thought that this would be the fundamental domain of gamma 1, 2, I know it has the double index because of plus minus the identity, but I thought this would be the fundamental domain, and that means that we should have this formula. And if we set k equal to unity, then we get a contradiction. On the other hand, what's going on here? I would like to say, assume G lies in of just gamma 1 of level 4, because that's of course by proposition 19 equal to this guy. Then I would like to say G divided by, it's theta squared. Which of course means it's a constant. However, if this has a 0, then we can't do it, and psi does have a 0 at the cusp 1/2. Meaning this idea doesn't work. That was actually theta to the 4th. But that must mean that this has a 0 as well. This stops me dead in my tracks, so I'll have to make a break and perhaps a cup of coffee, and then think it through, mull it over. That didn't take very long. First, I found my notes on how I derived the sum function. But before looking at it, I thought, well, let's look at the expansion of Q4 at 1/2, or theta to the 4th. At 1/2. And that means that theta squared plus minus 1/4 Q2 squared, meaning that the order of the zero at 1/2 theta is 1/2, which agrees with k equals unity. Oops, it should be a 1 here. This interesting factor here, since t lies in gamma 1 as well, we can't get a factor q12. Oh, even in theta itself, it's not any root of q. And at naught, it's already ramification index 4, so nothing can happen there. So that was open your mind here. So theta squared has actually order 1/2 at the cusp 1/2, and that's possible because in problem 2, where we derived all these interesting relations about which roots could occur, we actually used that -1 minus the identity was lying in the group. Or were we? Well, never mind. When we use, this is the matrix mapping infinity to 1/2, and when we do this, it actually lies in the one having chi being -1. What I was about, I thought it, but I didn't say it loud. Sorry about that. Now, assume so what I just argued was that the only zero we could have was at 1/2. And since k is unity, its order must be 1/2. Open your mind. And that means that both of them only have a simple 0 at 1/2. So this is actually a modular form. this may be a lot of powers, a lot of Q3 halves, etc. But when we divide by this, we do get an element in here anyway. We still get the expansion in terms of Q1 half. All right. And then they are proportional. Constant multiple. Right. Also that it actually lies there. I should think so. So that solves B. That was with a surprise. When k is even, we already have the answer. So I'll just repeat what we know about mk for m being even on the next page and then continue. I believe this was the result we got from the last problem. Well, that actually gives us the dimension for even numbers. Now, if this is an odd number, then this is the guy, and it has a 0 at 1/2. In M3 we can have one more 0, and in M5 we can have 2 more. And the one at infinity is f, and 1/2, that was phi squared. So it's theta to the 4th minus 16f times theta squared. And this has one guy that is asymmetric. So it's in M phi of chi. So that's the least, the cusp with the least zeros we can have. So we can use the same dimension of S 2k0 minus 1. Does that make sense? We'll see. We can divide it with this guy. Oh. I'll just write it. Then we divide it by this guy, which we called SO for odd cusp form. And then it's the two chi's divided by each other. Now what have I done here? It's a 5 and we already know the dimension of this space. Did I plus 1 up here? The dimension of this is k 2 times k minus 3 plus 1, it should be minus 2 then. And this is the same. Oops. I think I made it a little more complicated than necessary, but my result is the same. S8 gamma 1 of 4 is spanned by these two. Well, let's check the dimension. So that's 4 minus 2. That's 2, so it's two-dimensional. And we already have 2, but combining those are not quite obvious. So I think it's a better idea really to well, my first instinct is to verify that they lie in S8. This is trivial, it has naught as all the cusps. This is not at all. What is F? Of course it's not at all the cusps, so we just have to verify the correct transformation and that they are linearly independent. That should follow from their expansions at the cusps. So that's my program. What I'm thinking is that maybe this follows from proposition 17a, showing that this actually lies in gamma 2. Which is quite reasonable to believe. Maybe we already have shown it, by the way. So it's time for a break, and I'll see if we have this, otherwise I'll just do it. I found the function. We had already had it in proposition 20, that it's a cusp form in gamma naught of level 2, and that's a larger group in gamma of 2. So it's also a cusp form of gamma 2, and then apply proposition 17a. Now, how is that? I think it's with alpha equals 1. One naught naught 2, which shows that f of 2 set then lies in, it's still a cusp form of gamma naught of 4. So yeah, opposite. So we just need to show that they have distinct zeros, that they are not proportional. They're both cusp forms, of course, but we need their expansion at infinity. Oh, yeah, their expansions at infinity will differ. So the first term is Q24 to 8th, and here it's 2 times 8. That's Q. And f of 2 z will then go as Q squared plus. Oh, that was easy. Oh my God, I see the sun is coming in on the camera. Well, we've finished anyway, so it's a nice sunny day, as you see.